Why does a bright point source of light sometimes look like a starburst when viewed with a camera? The starburst pattern results from the diffraction of the light, a phenomenon we will explore in this lesson. When waves encounter an object, they bend around the edge of the object into the shadow region directly behind the object. This phenomenon is known as diffraction. Only if the object is larger than the wavelength of the wave will a significant shadow region form behind the object. Diffraction also occurs when waves encounter an opening. The waves bend around the edge of the opening. Which of these situations would produce greater diffraction? Correct. When the wavelength of the wave is greater than the opening size, the amount of diffraction is greater. Less diffraction occurs when the wave's wavelength is smaller than the opening size. One way to understand diffraction is by using Quiggins Principle. Quiggins Principle is that every point at the front of a wave can be thought of as the source of a smaller wave that spreads out in front of the wave at the same speed as the original wave. The new position of the wave is made up of the combined tangents to the smaller waves after the same time has elapsed. Now consider a wave moving through a small opening. Each point of the wave that passes through the opening can be thought of as a source of a new set of smaller waves. These new waves spread around the sides of the opening, and hence the wave is diffracted. Diffraction of light by the small diaphragm opening of a camera produces the familiar starburst pattern seen around a bright point source. Because the wavelengths of visible light are relatively short, it is difficult to make direct observations of light wave interference phenomena. It is also difficult to produce light from two coherent sources. During the early 19th century, Thomas Young solved these problems by using a single light source to illuminate two narrow, closely spaced slits. Light emerging from the two slits served as two coherent sources. When he passed light through the slits and projected it onto a screen, Young observed that a series of bright fringes appeared. This was in contrast to the two bright lines that some scientists expected would appear based on their assumption that light consists of a simple stream of particles. Young showed that light waves are diffracted by the slits. This causes the waves to spread out and interfere with one another. The resulting interference pattern projected on the screen consists of a bright central fringe flanked by a series of symmetrical light and dark fringes. Young's experiment proved the wave nature of light because interference and diffraction are phenomena that only occur with waves. The position of a bright fringe on the screen depends on the sine of the angle theta, through which the light is diffracted by a slit, and the distance between the slits. A dark fringe represents a region of maximum destructive interference. Under what conditions does it appear on the screen? Incorrect. Remember that to produce the maximum destructive interference, the two waves must be 1/2 wavelength out of phase. Try again. Correct. A dark fringe occurs when the path difference is an odd number of half wavelengths, as this results in the maximum destructive interference. If we perform this experiment with only one slit, we again obtain an interference pattern of light and dark fringes, though in this case, the bright central fringe is much wider. The position of a dark side fringe can be determined to be a function of the product of the slit width W and the sine of the angle theta. For a given wavelength, as the slit width decreases, the fringes become wider and the distance between them increases. The width of the central maximum is twice the width of the side fringes. What kind of interference pattern would result if we performed the experiment using many slits instead of one or two? Correct. Because of the increased number of slits, the number of bright fringe patterns would increase. Furthermore, there is more likelihood of two waves causing destructive interference, so the bright fringes would become sharper and narrower. A device to diffract light waves that consists of thousands of slits per centimeter is known as a diffraction grating. The conditions required a diffraction grating to produce bright fringes are the same as for the double slit setup. Because of the sharp patterns produced by diffraction gratings, they are used in research spectrometers for producing precise wavelengths of light.